Okay, so once again, welcome back to another topic. So for today's discussion is we will be discussing the introduction to mechanical waves as well as sound waves, and we have the beats and Doppler effect. Okay, so mechanical wave, if we will define what a mechanical wave is. So mechanical wave is a disturbance that travels through some material or substance which we call the medium for the wave. So when we form a wave, so let's say for example, you have a bowl of water. So if first is steady ang imo ang bowl with water, but once you disturb that with a few drops of water, so that substance or that material which we call the medium will form into ripples or what we now call the wave. So the wave or mechanical wave is the disturbance that travels through the material or the substance, which is the water that is put in a bowl, which we call the medium for the wave. Okay, so we have two types of mechanical waves. The first one is what we call the transverse wave. Now, what is a transverse wave? So, transverse wave, the displacements of the medium are perpendicular or transverse to the direction of travel of the wave along the medium. So, we have here an example of the motion of these types of mechanical waves. So, we have the first one is the transverse waves. So, as you can see here, if the motion of the wave is going to the right, so we can say na transverse wave siya if our motion or the motion of the particles are up and down or perpendicular with regards to the motion of the wave. So we have up, down, up, down, up, down. So we call that as transverse waves. Now, how about the second one? So the second one is what we call the longitudinal wave. So longitudinal wave, the motions of the particles of the medium are back and forth along the same direction that the wave travels. So going back here in our figure, for longitudinal wave, as you can see, again, the motion is going to, the wave motion is going to the right. So the particle motion or the motion of the particle is going back and forth. So going here and then going back and then going again here and also, so back and forth lang ang motion when we say longitudinal waves. So again, notice the difference between these two types of mechanical waves. So when we say transverse, the motion of the particle is up and down or perpendicular with regards to the motion of the wave. Whereas for the longitudinal waves, the motion is parallel to the motion of the wave, which is back and forth lang ang particle motion. Okay, so again, these are the two types of mechanical waves. Okay, so we also have this what we call the periodic waves. So periodic, it means repetitive or repetition. So each particle in the string also undergoes periodic motion as the wave propagates, thus forming a periodic wave. So the perfect example for a periodic wave is our pulse or ang atong heartbeat. So if you check your pulse in a monitor, kanang naa sa mga hospitals, so if you're admitted, so they will check your pulse if it is normal or if it is like consistent. So if your pulse, or if you can notice na if your pulse is normal, so you can see in the monitor na the motion of your pulse is repetitive or what we call periodic. So same as for periodic waves, it means na balik-balik or repetitive ang motion sa imuang wave. Okay, so now here are some of the things that we need to consider when it comes to periodic wave. So we have here the wavelength, we have wave speed, frequency, period, amplitude, and also angular frequency. Okay, so we must be familiar with each of this because they are also part of waves or periodic wave. Okay, so number one, we have the wavelength. So wavelength, the symbol for wavelength is we have right there. So we call it as lambda. So this is a Greek letter which is called lambda. So wavelength, if we will define wavelength, the wavelength is the length of one complete wave pattern, is the distance from one crest to the next, or from one throw to the next, or from any point to the corresponding point on the next repetition of the wave shape. Okay, so we have here a figure which indicates kung asa dapit or unsaon pag-measure sa wavelength sa isa ka wave. Okay, so the definition of wavelength mentions crest and also throw. So si crest, these are the peaks of your wave. So this four dots here are the crests of each wave, whereas si throw mo ni siya ang lowest nga part sa imo ang wave. So when we say wavelength, one wavelength or how we measure wavelength is from crest to crest or from throw to throw. So let's say for example, from here to here, so this is one measurement of a wavelength. And also, kung from throw to throw, from here to here, so this is also one measurement of wavelength, or what we call as the lambda. So that is wavelength. And then we have also what we call the wave speed. So wave speed, the symbol for wave speed is v, which is the same as the linear speed or the velocity. So wave speed is the product between wavelength and frequency. Okay, so we will now find later on the equations of some of these terms right here. Okay, so the next one is what we call the frequency. So a small letter f is the symbol for frequency. Frequency is the number of waves that pass a fixed point per unit time. So pila ka waves or number of waves that pass a fixed point per unit time. So let's say per second or per minute or per hour. So that is frequency. And then aside from frequency, we also have period. Period is the time it takes for the vibrating object to make one cycle or oscillation and return to its original position. So period is the time to make one cycle or one oscillation and returning to its original position. And then next is the amplitude. Capital letter A, ang symbol ni amplitude. Amplitude is the maximum displacement. So kibali kung sa projectile motion pa ni siya, mura ni siya og si maximum height. So amplitude is the maximum displacement or distance moved by a point on a vibrating body or a wave. So as you can see here, this is how we would measure the amplitude. So amplitude is from the x-axis, let's say, or along the x-axis. So amplitude is from here to the crest or the peak of our wave. So that is how we would measure for the amplitude. So from, again, gikan sa peak to the ground or to our x-axis. Okay. And then the last one is we have the angular frequency. So this symbol is what we call the omega. Now, basin mag-wonder mo nga nganong omega man siya nga. Si omega lahi man og symbol. Okay. So omega, we also have kung sa letters pa, we have the capital letters and the small letter. So si capital letter nga omega is katong familiar nato or ginakita nato, which is this one. So this is the capital letter for omega, and the small letter kibali for omega is we have this one. So we have two symbols for omega. So again, angular frequency, the symbol is omega or small letter W. So it measures the angular displacement per unit time. Okay. So now, here are the formulas or the equations of the terms that we have discussed. So we have first one is the wave speed, V. So V is equal to lambda, which is the wavelength, divided by T is the period. So again, wave speed V is equal to lambda divided by the period. And also the second one is we have frequency. So frequency is equal to 1 over period. Now, notice here na si wave speed is in terms, or we can also have it as lambda times 1 over t. So notice na 1 over period or 1 over t is frequency. So we can also rewrite wave speed V as lambda times the frequency. So we can also rewrite it as like this one. So if, again, depende kung unsay given sa problem. Okay. So aside from frequency and wave speed, we also have period. So si period is ang kabaliktaran ni frequency. Kung si frequency is 1 over period, si period is equal to 1 over frequency. Okay. And then, for the angular frequency, we have omega is equal to 2 times pi times the frequency. Or again, if we will substitute the frequency, which is 1 over t, we have omega is equal to 2 pi divided by the period, t. Okay. So how about the units of each of this one? So for the wave speed, we have meters per second, still the same for every speed, meters per second. For the frequency, we have this what we call the hertz. So si hertz, ang equivalent ni hertz is 1 over second. So 1 hertz is equal to 1 over second. And for the period, we have second or seconds. For the amplitude, we have meter or meters. And for the angular frequency, we have radians per second. Okay, again, the definition of angular frequency is the angular displacement per unit time. So that's why for the angular frequency, we have radians per second. So these are the equations of the terms that we have discussed, as well as the units of each of these terms. Okay, so now here we have an example. For our first example, we have sound waves are longitudinal waves in air. So the speed of sound depends on temperature. So at 20 degrees Celsius, it is 344 meters per second. So the question here is, what is the wavelength of a sound wave in air at 20 degrees Celsius if the frequency is 262 hertz? Okay, so let's write the given values first. The first one is the speed of sound, or V, which is equal to 344 meters per second. And then we also have the frequency, which is equal to 262 hertz. Okay, and then we are asked to solve for the wavelength lambda. Okay, so going back to our equations, so ang given nato is the speed of sound, V, as well as the frequency. So the best way to solve is to use this equation right here. V is equal to lambda times the frequency. So V is equal to lambda times frequency. So again, to solve for lambda, divide both sides with F or frequency so that makancel out ni siya. So we have lambda is equal to V over F. Okay, so we have the value of V as well as F, so we can solve for lambda or the wavelength. Okay, so we have 344 meters per second divided by 262 hertz. Okay, so para it's easier to cancel out the units, we will convert hertz in terms of second. So, di ba, take note na 1 hertz is equal to 1 over second. So, let's have 344 meters per second divided by 262 per second. So, our 1 over second sa numerator will be cancelled out with 1 over second in the denominator. So, the unit that is left is in terms of meter or meters. Okay, so if we will calculate this one, we have 344 divided by 262 is equal to 1.31 meters. So the wavelength of the sound wave, if the frequency is 262 hertz, is equal to 1.31 meters. Okay, so that is for our example regarding with how to solve for the wavelength given the speed of sound v as well as the frequency. Okay, so let's proceed with the sound waves. So if we will define sound, sound is a longitudinal wave in a medium. So again, when we say longitudinal wave, the motion of the particles are back and forth along the same direction of the motion of the wave. Okay, so aside from the sound, we also have this what we call the beats, or it is also known as the beat frequency. So frequency, so still the unit is in terms of hertz, basta frequency. So to solve for the beat frequency, it is the difference between the two frequencies. So notice here in the equation na we have two equations. The first one has no absolute value na bar, and the second one has an absolute value. Now, unsa may difference ani nila? So, this second equation will be used if the value of our f sub a is less than the value of our f sub b. Kaya nga naman, our beat frequency must be always positive. So, that's why, if lesser ang value sa atong f sub a compared to f sub b, the tendency is, when we get the difference, it becomes negative. So, to make it positive, we need an absolute value na bar. Okay, again, the purpose of the absolute value bar is to make the negative value a positive one. So, for example, we have our f sub a is 360 hertz. And our f sub b is 370 hertz. Okay, so if we want to get the beat frequency, we have f sub a minus f sub b. So we have 360 hertz minus 370 hertz. So we have 360 minus 370 is negative 10 hertz. But again, our beat frequency must always be a positive value. So that's why we need an absolute value bar, so that this 10 hertz, negative 10 hertz, will be positive. Okay, so the first equation also will be used if our f sub b is greater than the value, f sub a is greater than the value of our f sub b. So, for example, f sub a is 400 hertz and f sub b is 380 hertz. So, mas dako ang value ni f sub a kaysa ni f sub b. So, the answer or the beat frequency, when you get the difference, is the beat frequency is positive 20 hertz. So, that's why we have these two equations right here. The first one will be used if the value of your f sub a is greater than the value of your f sub b, and for the second equation with the absolute value bar will be used if the value of our f sub a is lesser than the value of our f sub b. So that is how we would solve for the bit frequency, which is again the difference between these two frequencies. Okay. So now we proceed to what we call the Doppler effect. So Doppler effect is an increase or decrease in the frequency of the sound, light, or other waves as the source and the listener either move toward or away from each other. Okay, so for the Doppler effect, we need to ang basihan nato are the motions of our source as well as our listener. Okay, so for the source, we will be using S for the source, and for the listener, we have L. So as you can see right here, in our general equation for the Doppler effect, we have F sub L, or the frequency heard by the listener, is equal to, we have V. V is the speed of sound. So for the speed of sound, by the way, it has a constant value. So V is equal to 344 meters per second. So again, this is the value of the speed of sound. But in some other cases, there are problems na they are providing the value of speed of sound. So if they are providing the speed of sound, let's say for example 340, 341, 342, so you will be using that one. So we will be using this value in case na the problem does not provide any value for the speed of sound. And then we need the value of speed of sound to solve for, let's say, the frequency, or even the speed of the listener or the source, or even the frequency of the source. So again, you can use 344 meters per second if ever lang na dili mag-provide si problem og value sa speed of sound. Okay, so going back to the equation, we have V sub L stands for the speed of the listener. V sub S is the speed of the source. Again, F sub L is the frequency of the listener, or the frequency heard by the listener. And then we have F sub S is the frequency of the source. Okay. And then V here is the speed of sound. Okay. So how about if we are asked to solve for the wavelength in front and behind of a moving source? So, to solve for the wavelength in front, we have wavelength in front is equal to V, which is the speed of sound, minus V sub S, or the speed of the source, divided by F sub S, or the frequency of the source. Whereas for the wavelength behind, if you're asked to solve for the wavelength behind a moving source, wavelength behind is equal to V plus V sub S divided by F sub S. So again, we can use this one if we are asked to solve for the wavelength in front or behind a moving source. Okay, so let's go back to our general equation of the Doppler effect. Okay, so notice here now we have this plus and minus signs in the numerator and the denominator. So, sa may pasabot ani. So, mag-change ni siya depending on the motion of your source and your listener. So, again, we need to consider the motion of your listener and your source. So, we need to draw a diagram para makita nato kung asa ang motion or asa padulong ang motion ni listener o asa padulong ang motion ni source. Okay, so to draw a diagram, On the left side is we have the listener. On the right side is we have the source. So let's say, for example, our listener is stationary. So when we say stationary, it is at rest or it is not moving. So, wala tay speed ni listener, or the speed of the listener is equal to 0 if it is not moving. Whereas si source is moving towards the listener or padulong siya kay listener. So notice nga si source is moving to the left. Okay. So how can we know if it is positive or negative? So positive atong gamiton if it is going to the right, and negative if it is moving to the left. So in this case, our source is moving to the left, so our V sub S is negative. Okay, so now, our equation for the Doppler effect now, given that our V sub L is 0 and our V sub S is negative, so we have F sub L is equal to V plus 0 divided by V minus V sub S times F sub S. So this is now our equation of the Doppler effect if our listener is stationary and our source is moving toward the listener. So again, no need to memorize each of these equations. What you need to do is just to draw a diagram, then determine if asa padulong si listener or asa padulong ang motion ni listener as well as the motion of the source, and then you draw an arrow depending on the motion, if it is going moving away or moving toward the source or the listener. And then after that, we can determine if our V sub L is positive, our V sub S is positive ba ka or negative or even 0. Okay, so we have another, let's try another situation. So let's say, let's draw a diagram. Our listener is moving towards the source and our source is stationary. So basta stationary, you will not draw any arrow. Okay, wala man siya nag-move. Okay, so V sub L is going to the right. So our V sub L is positive. Whereas our V sub S, since it is stationary, so V sub S is 0. So our formula now for the Doppler effect on this situation, we have F sub L is equal to V plus V sub L divided by V plus 0 times F sub S. Or we can also have that as V plus V sub L divided by V times F sub S. So this is now our equation to solve for the frequency heard by the listener if our listener is moving towards the source and our source is stationary. Okay, so another one, let's say our listener is moving away from the source and our source is moving away from the listener. Okay, so the listener is moving to the left, so that's moving to the negative x-axis or moving to the left. So we have V sub L is negative, whereas the source is moving to the right, so our V sub S is positive. So our equation now, we have F sub L is equal to V minus V sub L divided by V plus V sub S times F sub S. So this is our equation if this is our situation. Okay, so another one. So let's say our listener is moving toward the source and our source is moving toward the listener. So our listener is going to the right, so our V sub L is positive. And our source is moving to the left, so our V sub S is negative. Okay, so our equation now becomes F sub L is equal to V plus V sub L divided by V minus V sub S times F sub S. So again, it depends on the motion between your listener and your source kung unsa ang ato ang equation for the Doppler effect. But here, this is our general equation. So magdepende na dayon if ang ato ang V sub L baka is positive, negative, or 0, as well as si V sub S. So that's why we have this sample situations on how we would determine or how we would reconstruct our general equation for each situations. Okay, so we have here for our first example, a police car siren emits a sinusoidal wave of frequency F sub S which is equal to 300 Hertz. So obviously our siren or the police car siren is our source of the sound. So the speed of sound is 340 meters per second and the air is still. Okay, so before we start solving for A and B, let's write all the given values first. So the given are the frequency of the source, which is 300 Hertz, and also the speed of sound V, which is 340 meters per second. Okay, so for letter A, we need to find the wavelength. Wavelength, so meaning si lambda. Wavelength of the waves if the siren is at rest. Okay, so for us to be able to solve, so for letter A, we are asked to solve for the wavelength or C lambda. Now, how can we solve for lambda? So again, ang atoang equation na gamiton is the formula for the wave speed given the lambda and the frequency, which is, we have V is equal to lambda times the frequency. So, si lambda man ang atoang gipangita, so we need to divide both sides with F. So, lambda is equal to V over F. So, we have, in this case, F sub S. So, we have our value for V and also F sub S, so we can solve for the lambda or the wavelength of the waves if the siren is at rest. Okay? So, we have V is 340 meters per second divided by our F sub S is 300 Hertz. Okay, so we will transform Hertz in terms of second para it's easier to cancel out the units. So we have 340 meters per second divided by 300 per second. Okay, so ma-cancel out si 1 over second in the numerator as well as the 1 over second in the denominator. So, we are left with meter or meters. Okay. So, we have 340 divided by 300 is equal to 1.13 meters. So, this is the wavelength of the waves if the siren is at rest. Okay, so we are done with letter A. Now we proceed with letter B. So for letter B is we need to find the wavelengths of the waves in front and behind the siren if it is moving at 30 meters per second. So let's write again the given. So we have F sub S, which is 300 Hertz. We also have the speed of sound, which is 340 meters per second, as well as the speed of the siren or the source, which is equal to 30 meters per second. So we are asked to solve for the wavelengths in front and behind So, magamit na nato atong equation nga wavelength in front is equal to V minus V sub S divided by F sub S. And for the wavelength behind the source, the moving source, is we have V plus V sub S divided by F sub S. Okay, so let's start with the wavelength in front. So, we have V is 340 meters per second minus V sub S is 30 meters per second divided by F sub S, which is 300 hertz or 300 per second. Again, so that it will be easier to cancel out the units. So, makancel out gihapon, same, makancel out si 1 over second in the numerator and the denominator. So, we are left with meter, which is again the unit for the wavelength. Okay. So, for the wavelength in front, we have 340 minus 30 is equal to 310 divided by 300 is equal to, we have 1.03 meters. So, this is the wavelength in front. Now, how about for the wavelength behind? So, for the wavelength behind, we have 340 meters per second plus 30 meters per second divided by 300 hertz or 300 per second. So, the wavelength behind is, we have 340 plus 30 is 370 divided by 300, which is equal to 1.23 meters. So, these are the wavelengths of the waves in front and behind the siren if it is moving at 30 meters per second. So, that is how we would solve for the wavelength as well as the wavelength in front and behind a moving source. So, in this case, our source is the police car's siren. Okay, so we are done with example number 1. Now, we proceed to the second example. So, example number 2, we have here, if a listener L is at rest and the siren in our first example is moving away from the listener at 30 meters per second, the question here is, what frequency does the listener hear? Or we are asked to solve for F sub L. Okay, so for the given, we will be using the given in example number 1. We have F sub S is equal to 300 hertz. We also have the speed of sound, which is 340 meters per second. So, mo ni ang from the example number 1. So, and then we have the speed of the source, which is 30 meters per second. Okay, so let's draw a diagram between the listener and the source. Okay, let's say we have no figure right here, or we have no diagram between the listener and the source. So how can we determine the equation of the Doppler effect given only the word problem? So let's say without the figure. So we need to draw a diagram between your listener and your source. So dimension sa problem na si listener is at rest. So it means na our V sub L is 0. And the siren daw is moving away from the listener, which is going to the right. So our V sub S is positive. Okay, so to solve for the frequency heard by the listener, our equation now becomes F sub L is equal to V plus our V sub L is 0 divided by V plus V sub S times F sub S. Okay, so substituting the values, we have V is 340 meters per second divided by, again, 340 meters per second plus the V sub S is 30 meters per second times the frequency of the source, which is 300 hertz. Okay. So again, we have here 340 meters per second divided by 340 plus 30 is 370 meters per second multiplied with 300 hertz. So the unit meters per second will be cancelled out on both numerator and denominator. So we are left with the unit hertz, which is again the unit for frequency. Okay, so calculating, we have 340 divided by 370 times 300 is equal to 275.675, or we have 68 hertz. Okay, so this is the frequency that is heard by the listener if the source is moving away from the listener. So that is for our example number 2. Okay, so we proceed with another example, which is our example number 3. So another situation. So if the siren now is at rest and the listener is moving away from it. Okay, so let's write again the given first. So from the previous example, we have f sub s is 300 hertz, okay, since it's a continuation man, but with different situation. F sub s, we also have the speed of sound, which is 340 meters per second. So ang naad lang given is the speed of the listener, which is equal to 30 meters per second. Okay, so let's draw a diagram between the listener and the source para may balaan nato kung asa padulong ang motion ni listener and ni source. Okay, so the siren is at rest daw, so meaning it is not moving. So our V sub S is 0, whereas the listener is moving away from the source. So which means na si listener is going to the left. So our V sub L is negative. Okay, so the question is, what frequency does the listener hear? Okay, so our equation f sub L is equal to V minus V sub L divided by V plus our V sub S is 0 times f sub S. Okay, so substituting their corresponding values, we have V is 340 meters per second minus 30 meters per second, and then divided by, again, 340 meters per second times the f sub S, which is 300 hertz. Okay, 340 minus 30 is 310 meters per second divided by 340 meters per second multiplied with 300 hertz. So again, cancelled out si meters per second on both numerator and the denominator. So our f sub L now is, we have 310 divided by 340 times 300 is equal to 273.529, or we have 53 hertz. So this is now the frequency heard by the listener if our siren or if our source is at rest and our listener is moving away from the source. Okay, so that is for example number 3. And for the last example, again, it has the same given values from the previous examples. Let's write first para dili ta makalimot. So we have f sub S is again 300 hertz, and we have the speed of sound, which is 340 meters per second. Okay, so for our next situation, we have the siren is moving away from the listener. So let's draw a diagram. So the siren or the source is moving away from the listener, which is going to the right. with a speed of 45 meters per second. So, si V sub S is equal to 45 meters per second. And then, the listener is moving toward the siren or toward the source. So, it is also going to the right. So, both V sub L and V sub S are positive. So, V sub S is also positive. And then, V sub L is equal to 15 meters per second. So, again, the question here is, what frequency does the listener hear? Okay. So, again, the equation now is F sub L is equal to V plus V sub L divided by V plus V sub S times F sub S. Okay, so substituting their corresponding values, we have 340 meters per second plus V sub L is 15 meters per second divided by, again, 340 meters per second plus V sub S is 45 meters per second times 300 hertz. Okay. So here we have 340 plus 15 is we have 355 meters per second divided by 340 plus 45 is 385 meters per second. And then multiplied with F sub S, which is 300 hertz. So again, canceled out the unit meter per second. So we are left with hertz. Okay. So 355 divided by 385 and then multiplied it by 300. So the frequency heard by the listener on this case is equal to 276.623 or 276.62 hertz. So this is now the value of mo ni siya ang madungog na frequency sa imong listener if our source is moving away from the listener and our listener is moving toward the source. So the value of our frequency nga madungog ni listener is equal to 276.62. Okay, so I think that's it. So those are the examples as well as how to solve for the Doppler effect depending on the situations or the motions of your listener and your source. Thank you.